Hello everyone. This video is on the Knewton Alta assignment for section 6.5 part 1 called Basic Properties of Logarithms. So in this video I'm going to be going over a preview version of this assignment. So please understand that the questions I see in this video may not be the same questions that you see when you work on the assignment yourself. But the objectives are the same, the structure is similar, so I'm hoping that watching me do these here will help you in some way when you work on the assignment on your own. Now on your assignment page you should be seeing the title, the mastery bar telling you how far along you've gotten, the objectives, and it looks like there are 4 objectives for this particular assignment. Under the current objective, there should be a question related to that objective. And at the bottom of every question, you should be seeing a feedback button where you can send feedback to Knewton if you wish. You will not have this instructor cheat button, right? This is for instructors only. But you will have the more instruction button, right? If you're struggling with a topic, click on this, you'll be taken to a page with further reading or videos to study, and you'll be given questions related to that instruction, and completing those questions is another way to get through the assignment if you want. Alright, so the first objective I'm seeing is understand the basic properties of logarithms. Alright, so before I get into any questions here, I'm just going to go over a page where I write out all the properties of logarithms we're going to need for this particular assignment. And I would recommend memorizing these. Now I'm not going to write out the proofs of them or anything like that. You can read about that in a textbook. I'm just going to write out the properties that we're going to be using. So the properties of logarithms. Alright, so the first of these is just a pretty obvious one, I feel. If you take the logarithm base b of 1, the output is 0. Right, and again, if you can change the exponential form and try and understand why these things are true. Remember, the base b is some positive number. You take any positive number, raise it to the 0 power, you're going to get 1 back, right? You change this to exponential form, you'll see that it's true. Then we saw what are called the inverse properties, and these have come up in previous videos I've made as well from this chapter. The inverse properties. One is if you put, if you're taking a logarithm base b of, and then the input is a power of b, say b to the x power, then they just undo each other. It's just like composing inverses, and you're left with x as the output. You're left with that power in there. And it makes total sense when you change to exponential form. B to the x power is b to the x power. It's obvious. And then the other way around is if you have a base b and raise it to an exponent that's a logarithm with that same base, they'll just undo each other. B raised to the log base b of x would just be x. And again, it's easy to see that this is true if you change this to logarithmic form. You'd get log base b of x equals log base b of x. Alright, so these are called, the inverse properties. Alright, and then you have the product rule, or the product property, which I'll call number 4 here. So this is if you're taking a logarithm, log base b of a product, say x times y. Right, so the input is a product, a multiplication. Well, you can write this as an equivalent statement involving logarithms where it's the sum of the logarithms of each factor. So this is equivalent to the log base b of x plus the log base b of y. And this goes in the other direction as well. If you ever see the sum of two logarithms with the same base, you can put it together as a single log, and then the input is just the product of the two inputs of the sum. And then you have the quotient rule or quotient property. Sometimes this is called the fraction rule. Call this number 5 here. So this is if you have a logarithm base b, and then the input of that logarithm is a fraction, right? A quotient, a division problem, x divided by y. Well, you can rewrite this if you wish as well. This will be equivalent to a difference of logs, the log of the numerator, so the log base b of x, minus the log base b of the denominator. And again, it goes both ways. So if you ever see a subtraction of two logs, a difference of two logs with the same base, you can put them together as a single log, and the input of that new log is just the quotient of the two inputs of the logs from the difference. Alright, and then the final property we'll need for this video is a power rule, or the power property. Alright, so I'll call this 6. So this is if you have a logarithm, right, base b, of, say x to the r power. I think they use r in the book. I'm using r. I'm just trying to be consistent here. So you see how the input is a power. It's some base to a power. Well, you can write this as an equivalent expression with a logarithm by just pulling that power out front. R times, and then just the log base b of x to the first, or just x. So you see the exponent just comes outside and turns the expression into a product. R times a log. Now this one's tricky because people tend to pull powers out whenever they see them, no matter where they are. The only way this works is if the entire expression inside is raised to a single power. Alright, so the only way you can actually apply this power rule here is, once again, if the entire expression inside is raised to a single power. And then you can pull that power out front if you wish. Alright, so I'll keep referring back to this page as we go through the assignment. Now, first question, again, is on the understand the basic properties. It says, which of the following equations uses the inverse properties of logarithms correctly? So that was these. So once again, if you have the log base b of, and then some power of b to some power, you're left with just that power. Simple as that. And then the other inverse property is a base b raised to the log with that same base b of x is just x. They kind of undo each other when you compose them, logarithms and exponents. So let's just scroll through these here, right? Log base 4 of 11 to the 4th. Well, you can't apply the inverse property here, because if this is log base 4, in order to be able to apply one of those inverse properties, the base inside would also have to be 4, but the base inside is not 4, the exponent is. So this is not true. This does not apply the inverse property correctly. Now the next one does, you have 4 raised to the log base 4 of 11. So you have base 4, log base 4, they're the same base. So those undo each other, you're left with just 11. This is a correct application of one of those inverse properties. Here we have 4 raised to the log base 11. So the base on the log and the base on the base 4 are not the same. So this is an incorrect application of the inverse property. This line we have the log base 4 of a power of 4, right? 4 to the 11th. The base is 4 here, the base is 4 in the log, and you end up with just the power 11 as what it's equal to. This is correct, the correct application of one of those inverse properties. The next line we have 11 base 11 to the log base 4. So again, different bases. This is an incorrect application of the inverse properties. And then same thing for this last line. We have base 4 to the log base 11. The base 4 and the base on the log are different. So I can't apply those inverse properties. So the only two I highlighted are the only two that are correctly applying those inverse properties. And then after you submit an answer, you'll be told whether you're right or wrong, and then you'll be given some sort of answer explanation. Please read through the answer explanations just to make sure you understand why something was correct or incorrect, and hopefully you can learn from your mistakes for future questions. Alright, next, now we're to that product rule for logarithms. And they're saying to us here, use the product rule of logarithms to write the completely expanded expression equivalent to the natural log of 5 times 3 plus 7x. Make sure to use parentheses around your logarithm functions, right? Okay. And then when entering natural log, you just enter ln, right? Okay. So I'll write this out. And this one's referring to this property here, the product rule, product property. The log of a product is the sum of the logs of the factors. So the expression we're given is the natural log of a product, 5 times the quantity 3 plus 7x. So here I have, a product, some sort of multiplication going on inside the logarithm. So I can apply this product rule to, expand. They said, expand the expression. So according to the rule, it's just the natural log of the first factor, right? The natural log of 5 plus the natural log, right, the log of the second factor. The natural log of, now the second factor in this product is this 3 plus 7x. And that's it. This is all they're asking us to do here. Now, be careful. A common mistake I see is people try to distribute logs. They'll say the natural log of 3 plus 7x is, the natural log of 3 plus the natural log of 7x. That's not true. You can't distribute logs. Alright, this is false. This is bad. And I'll make that note. You can't distribute logarithms. I see that mistake made way too often. Alright, please don't do that. But yeah, so this is it. Log of the first factor plus log of the second factor of the product. And if there were 3 factors, I'd have plus the log of the third factor, and so on, right? It can extend to more than two factors. Alright, so down here, just natural log of 5 plus the natural log of 3 plus 7x, right? Make sure to close the parentheses on those things. Great. Alright, they're using a and b instead of x and y. Pardon me, but it's still the same property. Alright, so now that quotient rule. So now we're referring to this property, where you take the log of a fraction is going to be equivalent to the log of the numerator minus the log of the denominator. And I'll do that for this, they give us this one here, that we have the log base 6 of, and then a fraction, 2y minus 3 in the numerator, divided by, and then y in the denominator. But I do have a fraction, a quotient, some sort of division problem, inside the logarithm. Okay, so applying this rule, this should be equivalent to the log base 6 of the numerator, which is 2y minus 3, minus, right, for the fraction rule, the quotient rule, it's a difference, minus, and then the log base 6 of the denominator, y. And this is all they want. They just want us to apply that quotient rule to the log of a fraction. And that's what I'll type. Now don't forget the base 6, right? Log base 6 of the numerator, 2y minus 3, minus the log base 6 of the denominator y. And that's, again, that's all they want. Great. So still sticking with the quotient rule. Now this is actually going the other way. See, it says write the quotient, using the quotient rule of logarithms, write this expression as a single logarithm. You see here I have the difference of two logarithms, and I showed you, right, if you see the difference of two logarithms, you can write it as a single logarithm, the logarithm of a fraction, using this quotient rule. And that's what I'll do here. So we're given the log base 3 of 10x minus the log base 3 of 2. So this is exactly like the right side of my quotient rule, where x is 10x and y is 2. So I can apply the quotient rule and write this difference of two logs as a single log, right? So log base 3 of, and then inside this single log I put a fraction where the first input, this 10x, is the numerator, divided by, and then the second input from the difference, the 2, is the denominator. And there we go. Now of course we should also simplify this fraction. So this is going to be the log base 3 of 5x. And that's what they want, right? The simplified version of it. And you can test this stuff out with a calculator if you want. Plug in a value for x here, plug in that same value for x here, and the expression you started with should have the same value as this expression that you ended with. But I'll leave that to you to test out. Yeah, so they already have the log base 3 there for us. We don't need to just type that in. I just need to put the input 5x. Okay. Great. All right, and back to that basic property rule. Right, basically the inverse properties. So this one's kind of an easy one, right? If you remember those inverse properties, this is 2 raised to the log base 2 of 10. Well, remember, if you take a base b, raised to the log base b of x, you end up with just x. So 2 raised to the log base 2 of 10 is just going to be 10. So that's a quick one. 10. Alright. Now for the power rule. We haven't used that yet. So they're telling us here to use the power rule for logarithms to rewrite the following expression. So I have m times the log base 5 of 8. And that's like the right side of my power rule. Right, here is the power rule. If you see a number times a logarithm, you can put the number inside as the power on the input. So it's kind of going from right to left. So you see I have m times the log base 5 of 8. That's what we're given. I can kind of put this, this is like the right side here. I put this number in as the power on 8. This is equivalent to the log base 5 of 8 to the m power. And this is what they're asking me to type in after applying the power rule. So, yeah, so still log base 5, right? They have the log there, we just put the base in, and then and then the input's 8 raised to the capital M power. Okay. All right, so back to the product rule. All right, so here they give us a natural log of a sum, but they want us to use the product rule to, expand this. So that means I'm going to have to factor this. I need to rewrite the expression inside as a product. I can't use the product rule the way it looks right now, and I'll show you. All right, so back here. So again, I got the product rule written up for you. We're given the log, we're given the natural log base e of, and then the expression inside is 6a plus 9b. And they're saying use the product rule. Well, this is not a product right now. This is a sum. And if it's not a product and they ask us to use the product rule, that means we have to factor it. We have to write it as a product. So now I'm going to write the natural log of, and 6a plus 9b. Those two terms have a common factor of 3. So I factor a 3 out, and you have 3 times the quantity 2a plus 3b. And now I have a product. Alright, now I have a product inside the logarithm, where one factor is 3, and the other factor is, this quantity 2a plus 3b, and now I can apply the product rule. This is equivalent to the natural log of the first factor, 3, plus the natural log of the second factor, 2a plus 3b. Remember, I can't distribute logs. That's as simple as that gets. And this is what I'm doing here. This is what I'm typing. So natural log of 3 plus natural log of 2a plus 3b. And that should be good. Alright. So back to the power rule. Now this one I'll just kind of talk out because it's pretty simple. Nah, I should write it. I'm sorry. Alright, so we have 5 times the log of 2. We're working with the power rule this time. We're given 5 times the log of 2. And this is like that right side where you have a number times a logarithm. R times a logarithm. Well, you can put that number, if you wish, inside as the power on the input. So I put this 5 inside. This is equivalent to the log of 2 to the 5th power, which they're having us simplify this. 2 to the 5th power is 32. Alright, and you can use a calculator to verify this. Take 5 times the log base 10 of 2 and then punch in the log base 10 of 32, and you'll see you get the same exact thing. Alright, but we just want the log of 32, which is this choice here. Great. Alright, so back to those inverse properties, which are again, like the first question in the video, which of these lines applies the inverse property correctly. So look at the bases on the log and the base in the exponential statement. Base 8, they undo each other, you got 7, that's correct. Base 8, base 7, nope. Base 8, they undo each other, you end up with 7, this works, this is correct. Base 8, base 7, no. Base 7, the output's the input of the log, that's 8, that's correct. Base 8, base 7. So only the 3 I highlighted actually apply the inverse properties correctly. Great. And one more of these, same question. So base 5, base 9, no. Base 5, yes. Base 9, base 5, nope. Base 5, base 9, no. Base 5, base 9, no. Base 5, yes. Only 2 of these apply the inverse property correctly. Alright, so that objective's done. That was a pretty simple one, in my opinion. Alright, so now back to the product rule, and this is just like the last problem with the product rule, where I have to factor first, because it's not a product, it's a sum, and there is no sum rule. Alright, can't distribute logs, like I've been saying. Alright, so if I were to factor this, one factor would be 3, the other one would be x plus 2y. So it'd be log base 5 of 3 plus the log base 5 of x plus 2y, right? It's the log of one factor plus the log of the other. Once you write this as a product, once you write this as 3 times the quantity x plus 2y, you can then split it up like this using the product rule. Then one more of these. Now here the product is already given. One factor is 2x. Now it does say completely expand. Because when they say completely expand, that means you use the property, the properties until you can't use them anymore. So I should probably write this one out. Because they're trying. I think they're trying to trip you up with that word completely. Because we got the log base 5 of 2 times x times 8x plus 7, right? And this is a product. This is multiplication in here. Now there are 3 factors. I mean, you could say there are 2 with 2x and 8x plus 7, but 2 and x are also separate factors. But let me just do this one at a time. So say this is a factor and this is a factor, 2x and 8x plus 7. So using the product rule, this is equal to the log base 5 of 2x plus, and then the log base 5 of 8x plus 7. And then this is a product as well. See, 2 times x has 2 factors, 2 and x. So I can apply the product rule again and say this is the log base 5 of 2 plus the log base 5 of x. Right, that's the same thing as the log base 5 of 2x. Then this 8x plus 7, that can't be factored any further. So that's it. You're just going to leave that as the log base 5 of 8x plus 7. But I think this is what they meant by, when they say completely expand, they mean use the properties until you can't use them anymore. Right. That's what it means to completely expand. Right, so this one's going to have 3 terms. Log base 5 of 2 plus log base 5 of x plus log base 5 of 8x plus 7. And that should be completely expanded. The properties were used till I couldn't use them anymore. Alright, so that's it for the product rule. I got quotient rule. Alright, so this is again very simple. The quotient rule is the log of a fraction is the log of the numerator minus the log of the denominator, right? You can write it as a difference of two logs. So here I have the natural log of 2/7. That should be equivalent to the natural log of 2 minus the natural log of 7. And again, you can punch that into a calculator, both of those expressions, and see that you get the same value. And you should. Alright, and one more quotient rule. Again, very easy. You have a log of a fraction. Should be equivalent to the log of the numerator minus the log of the denominator. So this natural log of 6x minus 5 divided by x plus 4 is equivalent to the natural log of the numerator, 6x minus 5, minus the natural log of the denominator, x plus 4. And that should be it. Alright, so I got just the one more objective with the power rule left. And I've been doing this, right? If you have a number multiplied by a logarithm, that number can go inside as the power on the input. So this is equivalent to the log of 3 to the 4th power. Now 3 to the 4th power is 81. So the new input would be 81. And once again, you can punch these into calculators and see that they're exactly the same value. 4 times the log of 3, and then the log of 81, and you'll get the same thing back, I promise you. Alright, I should have just one more of these based on my progress. Alright, and this is the other way around finally. So I haven't done this kind of one yet, so come back out here to some paper. So here I'm given the log, base 10 of k to the 3rd power. That's like the left side of the power rule where, I have a logarithm, and then the input is, everything to 1 power, everything to the 3rd power. If that's the case, you can, if you wish, pull the power out front and make it a product. 3 times the log of just k, right? The power came out front. And this is what they want me to type in. Now they have the log there already, so I'm just typing the 3 and the k. So this would be equivalent to 3 times the log of k. And that's it. Alright, and that should be it for this preview version of this assignment. Now, like I said at the top of the video, the questions I see here may not be the same questions you see when you work on the assignment yourself, but the objectives are all the same, the structure is the same, or very similar. So I'm hoping that watching me do these here helps you in some way when you work on the assignment yourself. And thank you very much for watching.